Hello, good morning or afternoon. Thank you for joining us today. We're going to be getting started in just a moment. While folks get logged in for today's webinar, I just wanted to give some general housekeeping announcements. You are going to be muted during today's presentation. If you'd like to ask a question, please enter it into the online Q&A. We're going to be saving time at the end of the presentation to address as many questions as possible. This presentation is being recorded and will be made available on the COEH YouTube page and also on the LOHP site. We'll send out a link to that. And all participants who logged in today with their full registration email for the full live presentation, basically if you used the link that you were sent via your email address, we'll have a record of your attendance and you'll receive an email tomorrow with a link to the evaluation form, and that'll qualify you for a certificate of completion worth 1 continuing education contact hour. Once you complete that evaluation, you'll be able to access and print your certificate. Without further ado, it is my pleasure to introduce Robin Dewey, who's going to be introducing herself, the SASH program, and our speaker for today. Thank you for joining us.
Thank you, Michelle. So again, my name is Robin Dewey, and I'm a program coordinator with the Labor Occupational Health Program, which is part of UC Berkeley School of Public Health. And this webinar is being co-sponsored by COEH, where Michelle is from, and LOHP. And as part of our School Action for Safety and Health program, or SASH. SASH is a statewide initiative that helps school districts reduce injury and illness among school employees. Our focus is on the employees. And this presentation will review the importance of ventilation and filtration and discuss balancing energy consumption with indoor air quality and steps to improve classroom indoor air quality, including some best practices. So thank you all for being here. We are absolutely delighted to have Theresa Pistochini, sorry, here to present for us. Theresa is co-director of engineering at the UC Davis Energy Efficiency Institute and the Western Cooling Efficiency Center, and she has 14 years of experience in applied research in energy efficiency and building operation, primarily in the areas of HVAC and indoor air quality. She earned her master's degree from UC Davis and is a registered professional engineer in California. She's currently pursuing her PhD in mechanical engineering at UC Davis. So we're really happy to have her here. And so I'm going to turn it over to Theresa to do her presentation, and then we'll open it up for questions and answers. Thank you, Theresa.
Great, thank you. So here today to provide an update on best recommendations for improving indoor air quality in classrooms. All right, we already went over about me, but I put it in here for the slide deck for later. Just talking a little bit about the UC Davis Energy Efficiency Institute and the Western Cooling Efficiency Center. We're a research group at UC Davis, and we're primarily funded by public research through like the California Energy Commission and our California utilities and federal agencies, but we also try and work closely with industry so that our research can enter into practice. Okay, so objectives of what I'm going to cover today. So we'll just review the benefits of ventilation and filtration in classrooms and talk about best recommendations for those, including testing, adjusting, and balancing of airflows. Talk about carbon dioxide sensors as a tool for tracking ventilation performance, and talk about the trade-offs of ventilation and filtration as it relates to energy use and indoor air quality. Okay, so just to go over, start at the very top. What we're trying to do here is we're trying to control our indoor environment. And so there are several contaminants that originate from the indoors that we're concerned about. The one that's been the highlight over the past couple of years are respiratory aerosols. We've become more aware of how those transmit infectious disease with the COVID-19 pandemic. We're also very concerned about volatile organic compounds, which are or essentially are gas compounds that they're not particles, so they're not removed by filters, but they can have health impacts. And then carbon dioxide is emitted by building occupants, and we're going to talk more about that. There's some debate as to whether high carbon dioxide levels in and of themselves impact human performance, but regardless of whether or not that's true, using carbon dioxide sensors essentially serve as a measure of how the building is being ventilated. We have three different ways we can bring ventilation into a building. The first one is infiltration through the envelope. So our building envelopes have all kinds of leaks and cracks in them. And as the building code has been updated throughout the years, the building tightness has increased. So older buildings tend to be more leaky. We have natural ventilation, meaning we can open doors and windows. And then we have mechanical ventilation, which uses a fan to pull air from outside to inside. The benefit of mechanical ventilation is that we can filter it, whereas that just doesn't happen with infiltration and with open doors and windows. Outside, we have to be concerned about particulate matter, which has important implications for human health, and that can be generated. That those can be sort of more constant emissions from like vehicles and power generation and ag processes. But then we also have now the issue in the West of intermittent wildfire smoke. And it should be pointed out that regardless of where this outside air comes from, if we're trying to maintain an indoor environment, we have to heat and cool that air somehow if we want to stay comfortable. Oops. Okay, so the topic of respiratory aerosols that originates indoors. All I want to say about this really is that I think it's pretty well understood at this point. We all agree that these respiratory aerosols can build up inside of a classroom, and we can transmit them long range from one person to another person somewhere else in the classroom. There's a couple of ways to get rid of these particles. If we do nothing, eventually over time they'll settle, right? So like, for example, if we all leave the room and we come back the next day, right, those respiratory aerosols will essentially be of no concern. But while we're all in the classroom, we can ventilate, which means we can bring in outside air to dilute what's already inside, or we can run that air through a filter and pull out those particles. And if we just talk about this long range infection risk, there's a sort of a model that people use for modeling the risk of infection of having one index case and how likely it is to affect somebody else in the room. And that's called the modified Wells-Riley equation. And all I want to point out about this are a couple of variables so we understand why ventilation and filtration matter. So essentially the risk is a function of the exposure time. So how long we've been in that room with that infected person. And then the risk is reduced as we increase ventilation, and the risk is reduced as we increase filtration. So we're essentially pulling those respiratory aerosols out and reducing the concentration. So the risk is a function of the concentration of the aerosols in the room and the time that we're exposed. And then at some point, it basically just comes down to probability, chance that those aerosols infect a susceptible person in the room. So just on a real practical level, how do we ventilate and filter a classroom? And just the simplest form is we have an HVAC system. Now it could serve one classroom, it could serve multiple classrooms, but the general idea, the most common type of system is essentially a package type system, particularly in California. And so we basically get your return air back from the room. Some of it gets dumped outside. You mix in some outdoor air. So these two air streams mix. They go through a filter, they go through a fan, and then they go through your cooling coil or your heating coil or your furnace, and then they get conditioned and supplied to the room. We have 2 videos here that I just put a link to. And one describes the importance of ventilation and one describes the importance of filtration. And it covers all these, some of what I'm going to go over today. And so I just recommend sharing that with stakeholders. And the more YouTube hits I get, the cooler I am to my kids, right? So also on our website, just put here, summarize. I'm going to talk about all these things today, but basically the 5 things that school districts can do to improve indoor air quality in classrooms. This has been really, my message has been really consistent over the past 2 years since this all started. Actually, I was advocating for these things before the pandemic. Let the record show. But anyway, I'm going to try and give some more context today on things that have new things that have happened and things you might want to know about. But anyways, step 1, you want to test HVAC equipment to ensure that it's delivering the design ventilation rate. And there's a process to do that I'm going to talk about. 2, you have to be operating your fans on your HVAC systems to provide that outdoor air. That seems, obvious, but can be a problem. And then teachers need to understand the importance of those fans operating, and the fans are excessively noisy. That also needs to be addressed because sometimes, the noise is so problematic that, kids can't hear teachers over the noise. So really, it's technically feasible to have a ventilation fan that is not disruptive to the learning environment, but oftentimes that can be a problem. Use filters number 13 or better. And I'm going to talk about what that means, and change filters a couple times a year, every 3 to 4 months, to make sure airflow is maintained. Install carbon dioxide sensors into classrooms to monitor CO2 levels. I'll talk about that more as well. And then, if needed, supplement filtration with portable air cleaners. I have a link here on our website that has a report on portable air cleaners and things you should look for. And I talk about that a little bit more as well. Okay, so how much ventilation, right? So in terms of infection risk, more ventilation is better. Like so we saw recommendations early in the pandemic, as much outdoor air as possible. And we saw school districts just go open their outdoor air dampers all the way. So in my opinion, this isn't a sustainable solution because sometimes as 100% outside air can be really problematic from a thermal comfort perspective and an energy perspective. At some point, you might as well be sitting outside, right? So my recommendation here is to adjust HVAC systems to provide the design outdoor air rate, which in California is 15 CFM per person, and then use a certified test adjusting air balance technician to do that testing and provide that documentation. So I just put an example here. This is an example test report from from a tab technician. This particular one was certified. There's 3 agencies here that I recommend that have the credentials essentially to do these tests. And they actually go through and they measure for every single room the outside airflow rate for that room. And so this is a way for school districts and teachers essentially to have a way of documenting that this outside air is being provided, and it's a metric that we can use to make sure we're achieving the goals. So this is really important. And then in addition to having that mechanical ventilation, we can encourage teachers to open doors and windows when conditions permit, right? Like the outside air is clean, it's comfortable, it's not too noisy, right? But then at least teachers have the assurance, they've seen these reports, they have the assurance that they're getting that outdoor air, at least the minimum rate when their doors and windows are closed. So I want to talk about carbon dioxide monitoring. The test adjust and air balance report, that essentially gets the ventilation set up at one moment in time, right? And generally speaking, it should persist, right? But if maintenance staff unknowingly adjust it, if a mechanical component fails, if the filter gets really clogged, anyway, if something happens along the way, the question is, how would we know, right? Because that might have been a year since that system was tested. So carbon dioxide monitors provide real-time ventilation system monitoring. And so basically the way that this works is outside our CO2 levels are around 400 parts per million. Well, they're climbing, maybe they're 425. And then inside, occupants are exhaling CO2. And so that's essentially a tracer gas. And so if we have our room within our maximum occupant density, so if that room was designed for, and the ventilation system was set for 30 people, and we have no more than 30 people in that room, and everything is working correctly, those indoor carbon dioxide levels should stay below 1100 parts per million. And so this is a way for, and what I really advocate for is that that carbon dioxide reading should be displayed to the teacher and the occupants of the classroom, such that people can have like a visual check that the ventilation system is working. Best estimate on cost is somewhere between $500 and $750 a classroom to have a system that's installed, and generally and that has some connection to facilities, because generally facility managers, they're going to want to have that CO2 data going back to their building automation system or some central dashboard, such that they can flag issues perhaps even before they get a teacher complaint. Just want to mention there may be other types of sensors that are included in sensor packages. I, at this point, don't think there's a strong need for that. You can get particulate measurements indoors, but really generally you can also get particulate matter readings from outdoor EPA stations. There's not a whole lot you would do with that. There's not a whole lot of action you would take. Maybe you would know to close your windows potentially if that gets high. Volatile organic compound sensors that are included in low-cost packages are very poor accuracy. So I could like create a false sense of alarm for no reason. And so just really focusing on this CO2 is really the most useful measurement of continuous ventilation system monitoring. So I want to just make everyone aware of a website that we've developed at UC Davis with funding from the California Energy Commission. And I put the link here, energyproductevaluations.org. And so the goal of this project is to be the sort of like the Consumer Reports of energy products. And so this is like just launched, and it's a multi-institution. So actually it includes UC Berkeley and Lawrence Berkeley National Lab. And we're going to have like 15 categories of products, but one of the first categories that's up there is carbon dioxide sensors. And there's actually 15 products up there right now from all different manufacturers. And so I just want to encourage people to take a look at this and to make their districts aware that if they are going to invest in CO2 sensors, here's somewhere that they can get some unbiased performance data. And so on this website, we have for every product, this is just an example from one, we basically sample 10 sensors. We do some accuracy testing and show the errors. We look at the power consumption of those sensors, and we put together a list of technical specs for all the sensors that can be compared to each other. And we also have like a user experience section, which is sort of the experience of our researchers interacted with and using that product. Like, does it have a color display, or it's kind of what we experience using it that you might not quite pick up from just looking at the technical specs. Okay, and I want to talk about like why I'm so focused on the issue of tracking carbon dioxide and testing ventilation systems. So we did a project where we went to and monitored carbon dioxide in 100 classrooms across 11 schools in California. And then we surveyed all those teachers and we asked them questions about their satisfaction with the comfort in their classroom, like the temperature in the classroom, and then their perception of their indoor air quality. And what we found really surprised me. So basically, if we look at this plot right here, On the y-axis, we have the ventilation rate in that classroom, averaged by the teacher's satisfaction with their classroom temperature, and the red bar is heating season and the blue bar is cooling season. And what you can see here is that satisfaction increased as ventilation rate went down. So this is in liters per second per person. So all these classrooms on average were underventilated. So the California standard would be 7 liters a second per person. So this group was close, right? And this group was almost like half the ventilation standard. And so basically what our hypothesis here is that basically as you close down outdoor air dampers, the comfort of the classroom stabilizes, right? And so there's a motivation for facilities to close down outdoor air dampers in response to teachers' thermal comfort complaints. Because what happens is, like, for example, in the summer, we've got our outside air damper set how it's supposed to be, and then we're running the air conditioning system, and the air conditioning compressor is kicking on and going off, and kicking on and going off, and kicking on and going off. Well, every time it goes off, right, every time it cycles, that hot outdoor air is coming in the ventilation system and heating up. You get these hot drafts blowing on you, which causes discomfort. So then on the flip side, we asked teachers, basically, do you think you get sufficient fresh air from your HVAC system? And that was just a yes, no. And we looked at the CO2 levels in response to that question. And so you can see that the teachers that reported that, yes, they believe they get enough fresh air, had on average higher CO2 levels in terms of mean CO2 and peak CO2. And so basically, generally speaking, teachers with lower ventilation rates were more satisfied. And I should mention this was a study done pre-pandemic, so there was less awareness about ventilation, but in general, we are like poor ventilation sensors, right, as humans. And so when we have a thermostat on the wall, we can see what temperature it is, hopefully. And so it's also important to have that carbon dioxide sensor on the wall so that we start to understand, okay, ventilation is important too, and we need to try and achieve both of these targets, not just thermal comfort. And there's a link to the journal paper here if anybody is interested in reading more about this study. Okay, I'm going to switch gears to filters. So I mentioned that MERV 13 is recommended. I just want to talk a little bit about that. So here's a plot of mean particle diameter with filtration efficiency. And so you can see that it's actually these particles that are kind of in the middle, that are sort of in the range of 0.1 to 0.3 microns. These are the hardest to filter. The smaller ones, really tiny particles, are easily removed, and the large particles just collide with the filter fibers. But it's these ones in the middle that are difficult. And so we generally want to look at, when we're evaluating filters, we're looking at the filtration efficiency at this sort of 0.3 microns is the standard. And we care a lot about that because that's also the range of respiratory aerosols and the small particulate matter that can get down deep into our lungs. So you can see here MERV 8 versus MERV 13. MERV is the minimum efficiency reporting value. You can see we remove a much higher fraction every time the air goes through that filter with a MERV 13 filter. And so like 4 times, right? And so this is why this is so important. So the MERV 13 cost is not that significant. It's maybe $20 to $40 per classroom per year for that extra filter cost. And although there was a lot of discussion that, you know, school districts are concerned that their systems can't handle MERV 13, the resistance of the filter is actually pretty similar because the filter media just has additional surface area and additional pleats, and that reduces the resistance to the airstream. And so I think that's I think in most cases, any concern about that is generally a misunderstanding. And I just also included a link here on a study on filter pressure drop, if anybody's interested in that. And we also talk about this on our filtration video that I've linked here. Okay, so portable air cleaners. Generally speaking, if MERV 13 filters are in place and the ventilation system is configured, I would consider portable air cleaners sort of the last step in comparison to these sort of long-lasting facility improvements. But you know, they are effective. They are effective at removing particles and reducing exposure to smoke and reducing exposure to respiratory aerosols. They also are what I like about them is they're visible, right? They're something we can sort of all see and appreciate as a mitigation measure. The only thing I don't like is when I see school districts like only do that, right? And to me, this is like the last step, not the first step. In selecting portable air cleaners, the couple of things you want to look for, and I have the paper linked here, but you want to make sure in California it has to be certified by CARB for ozone safety and electrical safety. Doesn't mean that it works, right? Just means that it doesn't make ozone and it's not going to catch on fire. You want to look at the cost of that portable air cleaner per clean air rate delivered, CADR, clean air delivery rate, and its energy efficiency and its noise levels. So there's an Energy Star database that you can actually pull up a bunch of these metrics. And I talk all about that in the white paper. And in the white paper, I actually have like, I did it a while ago, but I actually put together a list of like metrics for 20 portable air cleaners that were available on Amazon. At this point, I would say avoid sort of extras in portable air cleaners, including UVC, bipolar ionization, or PCO technology, just due to lack of peer-reviewed data. Essentially, just stay with HEPA filters that have been more thoroughly characterized. And then the question is always, what about smoke? So if we maintain outdoor air rates at 15 CFM per person, you know, one of the questions is, well, should you just shut off all your outdoor air on a smoke day? And when we're concerned, if we have infectious disease spreading, influenza, COVID-19, we really can't, right? How do we do that? Because we're now increasing this indoor exposure. And so I think the best approach is to keep ventilating at this rate. An economizer, what an economizer does is when it's cool outside and the building is calling for cooling, it will open the outdoor air rate up to 100%. And that's great from a infectious disease perspective, but not if it's really smoky outside. So if possible, school districts disabling their economizers is a good idea, but sometimes you have to go into each and every unit, so it may be impractical. Filtration helps both indoor air quality and smoke, you know, for respiratory disease perspective and smoke. So again, that's why this filtration is so important. And I just have an example here. This is back from a fire in Northern California, the Camp Fire back in 2018. And this is this is a classroom, excuse me. This was 6 classrooms we were monitoring during the Camp Fire in the Sacramento area. And 3 classrooms had MERV 8 filters and 3 classrooms had MERV 13 filters, and both were being ventilated at this rate of 15 CFM per person. You can see here our outdoor air particulate matter and our indoor air particulate matter. And you can see that the air quality inside the MERV 13 classroom was much better. No portable air cleaners in this case either. And this was like a moderate smoke day. You can see outside was like 50 micrograms per meter cubed. And this was a more severe smoke day, outdoors 200 micrograms per meter cubed. And so anyway, you can see that, you know, we can really reduce by the concentration indoors by like half with just using that MERV 13 filter and still ventilating. I started to get concerned when, as far as I am not aware of any engineering solution that can make a classroom safe from an air quality perspective on like a really severe smoke day. When your outdoors start to reach that hazardous level like 250 micrograms per meter cubed, because your capacity can only filter so much, and if you're still trying to ventilate, you're just in a rock and a hard place. And so I think there needs to be some recognition that there are maybe some days where schools can just not operate, and that as of right now we don't have engineering solutions to make that possible. I think those days are really limited, but I think having some acceptance of that would help in planning. Because at some point kids are just safer at home, like not trying to be transported to school in severe smoke. And also at home, we can try and, really seal doors and windows and reduce ventilation without being concerned about spreading infectious disease. Like within our household, that's a much less of an issue than within an entire classroom. Okay, and so finally, I just want to talk a little bit more about this issue of how we can think about how ventilation and filtration impact both, like quantitatively impact energy use and long-range infectious disease transmission. Because to reduce infection, we can raise outdoor air rates, we can improve filtration, and we can use portable air cleaners, but all those things potentially are going to use more energy. And the impact of that is going to vary depending on where we are in the United States. So there's a lot of details here, and we're in the process of making some revisions and publishing this. So I don't think that's too far off. But if you're really interested and want like a copy of the submitted paper, please let me know. But basically we have a building model. So we're basically simulating a building in an energy modeling software called Energy Plus. And we're looking at basically the HVAC energy use for energy consumption and thermal comfort. And then we're also looking at transmission risk using that modified Wells-Riley model that I showed you earlier. And so there's a lot of information here, but I'll try and summarize what happens. So here I've got 13 cities I'm going to show you, but here's the first 7. So basically what we do is we look at annual electricity consumption as we increase ventilation rate here along the x-axis. And as I mentioned earlier, 7 is the standard. And so, for example, if we use an economizer, which I mentioned earlier, like if we're calling for cooling and it's cool outside, we can economize, we can bring in that outside air for cooling. We get a little extra ventilation when we do that, particularly in dry climates. So like Phoenix, you can see if I use an economizer, I get 10.8 liters per second per person ventilation, but my energy use is actually less than if I only had 7. So economizers are really great because they both decrease our energy consumption and they decrease our infectious disease risk. But anyway, you can see basically what happens like in somewhere like Miami, right? As we increase outdoor air rate, our cooling energy use just goes up. And I don't show it here, but when we get to 100% outdoor air in most of these climates, we're actually unable to meet the cooling load with typically sized HVAC equipment. And then we have all this these hours that don't meet the thermostat set points, which is just not, it's just not going to work in the long run. So basically we're just analyzing here. I also have here the energy use from a portable air cleaner. You can see is pretty small. And then we have the energy use from the HVAC fan and this little black bar, this tiny, tiny little black bar. That's the additional energy used by a MERV 13 filter compared to a MERV 8. So just having the fan and the MERV 8 filter, like any filter, just the fan system itself, moving the air through all that ductwork, it's a big chunk of the energy use in a classroom. And if we just upgrade that filter and we have a little extra resistance, we just use this tiny amount of energy. So the MERV 13 filter is just really good bang for the buck. I just want to point out, so Los Angeles and San Francisco, those are very interesting cases. In those situations, we actually potentially energy decreases when we increase ventilation, meaning that our cooling loads in our classrooms are quite high and the air outside is so temperate that we can actually get all this extra ventilation in these coastal climates without having an energy impact. And so that's important for those limited climates, right? Because we do have a lot there is a lot of population along the coast. So I think that's an interesting finding. Similar results as we go north and we go east. You can see heating, electricity just goes through the roof as we start to increase ventilation rates. So, and again, you can see what we really see here is that the filtration measures make so much more sense in compared to just increasing ventilation. And so then I want to just shift here and look at infectious disease risk. So this is using that Wells-Riley model. This is what I've calculated here is the probability that if you have one infectious person in 26 susceptible people, so 27 students in the classroom, one's infected, what's the probability that that person will infect one other person in one school day, at least one other person in one school day? And so you can see those probabilities are on the order of like 2 to 7%. Obviously, this is just a model. It's most useful for like relative comparisons instead of looking at these absolute numbers, because the diseases are, I mean, the transmissibility is changing all the time as mutations happen, right? But what we can see here is that if we have, so this is increasing ventilation rate. So as we increase ventilation rate, you can see that the infection probability drops as we would expect. But then if we go to a MERV 13 filter that's filtering a higher percentage of those particles, increasing ventilation doesn't do as much, because every time we recirculate that air through that filter, we pull out a lot of those particles. And then if we add in-room filtration, right, we tighten that down even more. And I should mention the amount of in-room filtration portable air cleaners that I've modeled here is pretty substantial. This would be like 2 sort of large portable air cleaning units. I think around 600 CFM for that classroom. And this is just showing sort of what happens with energy as we go through those same parameters. Now, I've talked a little bit about economizers, but I just wanted to bring that up one more time here. So this shows for every city, if we have an economizer from that model, how much increased ventilation above that 7 liters per second per person we would get for the economizer, and then how much energy we would save. And so you can see that economizers, as I mentioned, are really powerful tools in the hot, dry climates: Phoenix, Los Angeles, Las Vegas, Albuquerque, Denver. And economizers economizer controllers are not particularly expensive, but they're actually not that widely used, and a lot of times they're not necessarily configured correctly, which is why that test, adjust, and air balance process I mentioned earlier also tests and configures the economizer. So this is a way we can both increase ventilation and save energy. Okay, so conclusions, as we'd expect, 100% outdoor air results in sort of significant thermal discomfort, unless you're in Los Angeles or San Francisco. 15 CFM is a reasonable ventilation rate, which is based on current recommendations and current code. Economizers save energy and reduce infectious disease transmission. MERV 13 is absolutely sort of the best bang for your buck in terms of filtration to reduce infectious disease transmission, and portable air cleaners, as I mentioned, are an additional reasonable step. And I've just summarized here for everybody the recommended priorities for school districts. So test, adjust, and balance systems, use windows and doors when possible for extra ventilation, install MERV 13 or better filters, potentially use portable air cleaners, and monitor indoor CO2 levels. And I'll just mention for further research that I'm working on at UC Davis is to look at how to design ventilation controllers such that they can essentially automatically handle outdoor pollution and smoke days, and balance both energy and infectious disease and outdoor pollution sort of all in one package without any intervention for facilities or teachers. And that's it. So I will take questions now.
Thank you so much, Theresa. That was wonderful. And we do have one question in the Q&A section that I'll just read to you and maybe you can respond to. If CO sensor readings are tied to building automation systems, would it be necessary to have a readout in the classroom given that teachers wouldn't understand or appreciate normal fluctuations in 1100 ppm levels?
I think transparency is really important. And some teachers may not understand or appreciate, but many will. And, you know, eventually, and I understand that that might cause some stress for facilities initially, right? As that has to all be communicated. But at the end of the day, I think that's the best place to land.
Thank you. And then I wanted to see if you had anything more to add on this, because I know you did talk about it, but we also had a comment in the chat just about how you know, challenging it is to have both worrying about wildfire smoke and ventilation issues, outdoor air and then indoor air. And so we were wondering if there should be more education that happens maybe for coaches and others about when, you know, about student respiratory hazards and when they shouldn't be exercising outside, et cetera. So anything more you wanted to add about what we should be doing in terms of education of the school communities?
Yeah, I think, I mean, that's the other reason I was talking about today. I've been in several conversations where, you know, this idea of that the school should be like the safe haven on a severe smoke day. Like somehow we will make that school safe and we will operate that school. And it's like, can we really do that? I'm not aware of a way to do that, right? On a really severe smoke day, transporting students back and forth to school, shutting down ventilation completely when you have 30 students from different households in a classroom is just problematic. I don't see any way around it. And so I think we can operate in pretty moderate smoke, right? If we have the right filtration. But at some point there has to be, in my opinion, there should be a threshold when, like in the Northeast, there's a point at which we say that's a snow day, right? Like we're not going to risk student lives to get them to school. Like at some point they're just safer at home. And I think those days are rare, right? But they do happen. And I think this is just something that is going to be a continual problem here on the West Coast, and that we just have to accept instead of trying to come up with a solution that does not exist at this time. And yeah, the coaches, I have athletes, kids, and yeah, that drives me crazy. I've had a few words with coaches. I don't know what to say about that. It seems like some of the organizations like CIF, you know, are pretty progressive, but it all comes down to that. I really should go like to the head of those coaching, like AYSO, I found to be pretty responsible, for example, but then occasionally you get like certain clubs that just, they say, well, we'll run it, we'll let the parents decide, or we'll let the kids decide. But I think that's, you know, it's not really leading in that area, right? Because oftentimes kids feel pressured in a sport, in a competitive sport, like if the practice is open, that they should be there, and it's not very equitable, right? Also to kids that suffer from asthma, right? To run that practice And then those kids are like left out and don't get that coaching, you don't get that opportunity. So I think I don't really know how to address that per se, but I've definitely noticed that. That's definitely true. And I think there's also, I haven't really looked at the research recently on this, but there's been some concern hypothesis that like, does that particulate matter exposure, does that increase our risk for respiratory illnesses, like poor outcomes? And so that's sort of an open question that I don't know the answer to either.
Okay, thank you. Okay, we have another few questions. First one is, what do you think about the AirNet CO2 monitor?
I am not familiar with that one, but I will put that on my list of things that I go look at. We're going to keep continually adding to that website. So if there are things that people are interested in,
okay. And then another question, in the Northeast, as you were just talking, we have a significant change in amount of recirculated air due to winter and heating costs. What do you recommend for removal of CO2 or other contaminants outside of PM for recirculated air?
Yeah, the problem is that like the reason that I mentioned this 15 CFM, and that's so the standards vary a little bit by state, but generally speaking, you're going to land about at 15 CFM per person for a classroom, and that's building code, right? That's a minimum building code requirement, and so that should be delivered anywhere, anytime, regardless of the weather. And building engineers, when they design those HVAC systems, they design them to be able to provide enough heating or cooling on the coldest days at that ventilation rate. So really there should be no probable, no, now you might be, one of the issues is that because of the pandemic, people started opening up outdoor areas all the way. And in that situation, you can't meet the building load, but you should be able to meet the minimum ventilation rate of 15 CFM per person. And so the reason we still need that is even if you could filter 100% of the particles, you cannot, using standard filtration technology, you cannot get rid of those volatile organic compounds from inside the classroom. So that's, chemicals off-gassing from materials like formaldehyde and, we have chemical sources all the time. We have cleaning agents, we have hand sanitizer, we have whiteboard markers, we have air fresheners. Don't use air fresheners, by the way. We have deodorant, we have smelly kids, we have all kinds of things that are not particles, right? And so we have to have that minimum rate, regardless of filtration. And there's nothing practical. You could use carbon filtration to remove some of it, but it's not cost effective. Or widely, it's just not widely used. So that's why we have those minimum outside air rates. You can't remove carbon dioxide. You can, but not practically.
Mm-hmm. Okay, so then just a point of clarification, the CO2 monitor that was asked about is the AirNet 4, just so you have that down. And then we had a clarifying question as well. Why is it safer at home since the AQI is probably the same at home?
Oh, because then if we're just with our immediate household, we can close all our doors and windows and shut off any ventilation sources. And then we're reducing that outdoor air we're bringing into our house. And then ideally, now here's an equity issue, but ideally homes would have access to some sort of portable filtration. But that's the issue. We're not sealing a building with 30 students that could potentially be spreading infectious disease among each other. We're just now limiting to our household. And then you also don't have the transportation to and from school. Air change rates in vehicles are quite high. So the pollution exposure in vehicles is not great either.
Okay,
and recess and lunch and going from one classroom to the other and all of that.
Okay, thank you. So are there other questions that people would like to ask? Please post them in the Q&A. This is really helpful, Theresa. Thank you.
Sure.
Okay, and then Claire says in the chat, pollen is also a great thing to want to filter out. Just as
I agree.
Yeah. Okay, just waiting to see if there are any other questions. Let me check again. Okay, Theresa, any other last thoughts or, messages you want to convey?
No, if Sherry wants to, did you provide my email address anywhere? If Sherry wants to send me an email about that AirNet 4, I can try and take a quick look and see what that one's about.
Okay.
But I should mention, just because it's not on our list doesn't mean that it's not useful. We just only have rated some of them. And on our website, we have some application guidance and things you can look for that could help people sort of look at ones that we haven't tested.
And also, thank you, Allie. Thank you also for posting in all the other links in the chat. So thanks for doing that. So we did have a question. And that is that you mentioned not to use indoor air fresheners, but what else can we use to make the home smell nice?
Interesting. So really any scent is a volatile organic compound. The scents are created by chemicals. Our perception of an odor is a response to a chemical. And so I personally don't. Now, not all scents are going to be harmful, but how would you really know that? And so like candle burning, right? Like that creates both volatile organic compounds and it's certainly not helping your health. Let's put it that way. We don't know if it's harming your health, but it's not helpful in any way. I mean, I don't have any scented products in my home as best I can. I mean, I'm not a Nazi about it, but I don't go looking for scents personally.
Mm-hmm.
So maybe bake some cookies, cut an orange. I'm not sure, but yeah. And it's really hard because just many of these consumer products are not well regulated, and you often don't even know what's in them. And so it's just like our knowledge on some of that, what's in there, and the exposure is just really hard to even quantify.
Mm-hmm. And then a little bit more information about the AirNet 4. Just, it's a standalone portable CO2 monitor.
I guess I should mention, sometimes school districts might have CO2 monitors that they might move around, which is fine. But you have to have the people in the room to generate the CO2 to get a valid measurement, and they need to have been in there for like an hour. So if a district is going to move a monitor, you would want to advocate that you get a couple of hours of monitoring. Like there's been stories of facility managers going through empty classrooms and going, no CO2 here, which this is not useful.
Mm-hmm.
I think everybody understands that at this point, but just in case. But yeah, portable ones, you can move them from classroom to classroom if you have the if you want to do that. And yeah, if anybody wants to, we were not talking about houses today, but yeah, if cooking in particular matter are very interesting. I've done all kinds of experiments in my own home. So right. Particulate matter sensors are really interesting, right? They're not really that useful in a classroom because we don't generate a lot of particulate matter in a classroom, but it's very interesting in a home with cooking.
Yeah.
And vent hoods are your friend, and open windows.
Yeah, and there are people in the chat who are totally agreeing with you. The cooking rapidly.
Yeah, I'm reading this.
Oh, you're seeing it too. Okay.
Yeah,
I didn't know if you were. Okay. Yes, great.
Okay.
All right. Well, Theresa, thank you so much. If there are no other questions, I think we'll close this webinar, and we just really appreciate everything that you shared with us and all of the links, etc. So thank you very much. And Michelle, I don't know if there's anything you wanted to add before we close.
No, well, thank you everyone for joining us today. You'll receive an email with a link to the evaluation and certificate at noon tomorrow. It sends 24 hours automatically after the webinar. So be on the lookout for that email, and thank you for joining us. Bye,
Thank you.
everyone.